Namaste. In the previous class, we looked at the chemical properties of alcohols and phenols. We started with the first property, which was acidic nature. We said that alcohols and phenols are acidic in nature because they can give away H+. We also looked at who's a stronger acid. Phenol is a stronger acid than alcohol because of resonance stabilization of the phenoxide ion. Thereby, phenol gives away more H plus in comparison with an alcohol. We also looked at relative stabilities of various alcohols and relative stabilities of various substituted phenols. Primarily, the deciding factor is the number of groups that are there, whether they are electron releasing in nature or whether they are electron withdrawing in nature. All these will determine whether the acid is strong or weak. Today, we look at the second reaction under the type cleavage of OH bond, and this reaction is called as esterification reaction. Now, as the name itself indicates, this is a reaction where we are going to synthesize an ester. This is what is esterification reaction. Now, who is an ester? Esters have the general formula RCOO R dash. So if through any reaction we get an RCOO R dash as the product, we call such a reaction as an esterification reaction. Now, one of the common ways in which we can prepare an ester is by the reaction of an alcohol with a carboxylic acid. So hence, we study this as the property of an alcohol. And here, which bond is broken? The OH bond is broken, which means H plus is removed from an alcohol. So what is happening with the carboxylic acid then? From the carboxylic acid, OH minus is being removed. So I have OH minus being removed from the acid, H plus removed from the alcohol like this as water, and this is facilitated by an acid. H2SO4 facilitates this removal of H2O. The moment I remove water from this, what remains is this R dash COOR, which is what is my ester. We have an example here so that you can understand better. If I take methyl alcohol and react it with acetic acid in the presence of an acid as a catalyst, there is removal of water to give us the ester methyl acetate. Yeah, so the ester is methyl acetate. Now this is acetate and I have methyl. Clear? So this is obtained from the acid part. Clear? Hence this is the acetate and this is methyl obtained from the alcohol part, therefore giving us the compound methyl acetate. Now, I want you to observe one thing. If at all you were sharp enough to understand, to observe, alcohol is giving away what? It is giving away H plus. A carboxylic acid is giving away what? A carboxylic acid is giving away OH minus. Now, does something ring your bell here? Carboxylic acid, being an acid, should actually be giving away H plus because the name itself is an acid. An acid is somebody who gives away H plus. And we have also seen in the previous case that carboxylic acids are stronger acids than alcohols. So if I have a carboxylic acid and an alcohol, naturally a carboxylic acid should be the one which should give away H plus. If this is giving away H plus, then naturally OH minus should be obtained from alcohol. But what's happening in esterification is not that. H plus is being released by the alcohol and OH minus is being removed from the carboxylic acid. So this goes beyond our understanding or against our understanding. A carboxylic acid is behaving like a base and an alcohol is behaving like an acid. Why is this so? This is your first homework. Now, you might be wondering, sir, this is just the first reaction and you're giving me a homework? Yes. The idea is very simple. The moment we have a problem at hand, it's important that we go ahead and tackle that problem. So take this as homework. Why does a carboxylic acid behave as a base and an alcohol behaves as an acid in an esterification reaction? And by the way, this is a very important reaction both for your PU and competitive. In fact, this question has been asked a lot of times in competitive. H plus is removed from which of the following during an esterification reaction? A. Carboxylic acid. B. Alcohol. C. H2SO4. D. None of the above. Say, for example, a question like this that is asked. If we do not have an understanding about esterification reaction, naturally we'll go ahead and mark option A as the answer, because in our mind, carboxylic acid is an acid and it is something that will give away H plus. But in esterification, that is not the case. So I want you to go ahead, find out why this happens. Clear? So this is what is esterification. One of the methods of esterification involves an alcohol reacting with a carboxylic acid in the presence of another strong acid, giving us an ester. We can also prepare an ester starting from an acid chloride, which is also called as an acyl chloride, or acid anhydride. Now, these are two other compounds which can react with my alcohol to give us the corresponding acid. Now, even here, the logic is very similar. I will have H plus taking away Cl minus to go out as HCl. Now, what remains? RCOOR dash will remain, which is nothing but a ester. Now, same logic is applicable even here as well. Even here, I have RCOOCOR, which is nothing but my acid anhydride. Like in the previous case, H plus is removed from here, and that H plus is taken away by this RCOO to become the acid, RCOOH. Whoever remains there, RCOOR dash becomes our ester. Clear? So the logic remains the same. It is just that we can also use an acid chloride as well as an acid anhydride for us to get the corresponding ester. Clear? So we have seen three cases or three situations where we can get an ester. The common reagent being alcohol. Alcohols can either react with a carboxylic acid, or it can react with an acid chloride, or it can react with an acid anhydride to give us an ester. Now, one of the things that we discussed in the beginning of this chapter is, why do we need to study all these compounds? What is the need for me to study all these reactions? Now, I would have been better off without studying, without remembering these reactions. Organic chemistry is something that we can live without. It's probably something that is running in many people's minds. But unfortunately, organic chemistry has a lot to offer to humanity. And that's one of the reasons why we need to focus more on organic chemistry than anything else. Now, why esterification? Esterification is a very important reaction because it gives us one of the most commonly used drugs known to man. Salicylic acid. This is salicylic acid, where I have a COOH group attached to phenol. This is made to react with acetic anhydride. No, this is acetic anhydride. When it reacts in the presence of an acid, esterification takes place. So I will have H plus removed from here and CH3CO removed from here as carboxylic acid, which is acetic acid. Whatever remains there will combine with oxygen to form this ester. This ester is called acetyl salicylic acid because I have an acetyl group, CH3CO group, that has got substituted to salicylic acid. Hence, this is called as acetyl salicylic acid. This commonly is called as aspirin. Aspirin is one of the most commonly used drugs in the world today. If we did not understand esterification, if we did not focus on esterification, probably we would not be in a position to produce this drug, which is used extensively. So this is preparation of aspirin. I'll just keep the slide open for a moment if at all anybody would like to write down. As I've already told you, I'll be sharing this PPT at the end of the chapter. I will also be uploading this onto my YouTube channel so that you can retrieve, you can look at the videos at any given point of time, just to ensure that your focus right now remains on understanding rather than just blindly copying down. All right. Yeah. Those were the two reactions which came under the first category, reactions involving cleavage of the OH bond. Now coming to the second type of reactions, reactions which involve the cleavage of CO bond in alcohols. Oh, I have an ROH. So here we are trying to break the bond between C and O. Now this is seen only in alcohols, very important. I do not see cleavage of CO bond in the case of a phenol because we have studied this in the past as well. The oxygen is attached to benzene in the case of phenol, and I cannot create a scenario where a bond is broken and there is a positive charge on the benzene ring, on the carbon of the benzene ring. That ion is highly unstable, hence the driving force, necessary driving force, is not there for the reaction to happen. Thereby phenols do not undergo these type of reactions where the bond is broken between carbon and oxygen. Hence, whatever reaction that we would study under this type here, all of these will only be seen in the case of alcohols and not in phenols. And when we look at the relative reactivity of alcohols for such a cleavage, the order is as shown below. When you observe the order, methyl alcohol is less reactive compared to a primary alcohol. Now, we have already seen what a primary alcohol is. A primary alcohol is an alcohol where OH is attached to a carbon, which is in turn attached to one more carbon atom. This alcohol is in turn less reactive than a secondary alcohol. Now, who is a secondary alcohol? OH is attached to a carbon, which is in turn attached to two more carbon atoms. Now, this alcohol is less reactive than a tertiary alcohol. Now, who is a tertiary alcohol? OH is attached to a carbon, which is in turn attached to three more carbon atoms, which means more the number of R groups attached to the carbon having the OH, greater is the reactivity towards breakage of the CO bond. Now, why is that so? Answer lies here. It's because of plus I effect or electron releasing inductive effect. We have seen that R groups are electron releasing in nature. More R groups attached to a carbon, more is the electron density on this carbon and on oxygen. Thereby, it is easy for us to break the bond. Less the number of R groups, less the electron density on carbon and oxygen, and more difficult for us to break the bond. And when we look at methyl alcohol, It's pretty straightforward. All three are hydrogens. Hydrogens are neither electron releasing nor are they electron withdrawing. So therefore, they will not contribute to the electron density on carbon and oxygen, thereby making them the least reactive. So this is a very important aspect that I want you to understand. Reactions involving cleavage of CO bond, all alcohols do not react the same. Tertiary alcohols are the most reactive, followed by secondary, followed by primary, followed by methyl. This is because of plus I effect. All right, let's look at the first type or first reaction under this. Now I've clubbed 3-4 reactions here under the first type because the way the reaction happens is quite similar, and the products are similar too. Hence, I have clubbed all of them under one single category. Now these are reactions of alcohols with hydrogen halides, phosphorus halides, and thionyl chloride. Now, all these reactions are something that you have come across in the previous chapter. In the previous chapter, haloalkanes, you used all these reactions in preparation of alkyl halides. Now, you studied all of these reactions in preparation of alkyl halides. Here, we are studying these as properties. That's it. So, hence, I will not spend more time on this slide. It's just that I'll just brush through the reactions so that you understand. The first reaction is reaction of an alcohol with HX or a hydrogen halide. Reaction is simple. H takes away OH from here to go out as water. Who remains? R and X. They form the alkyl halide. The second one, alcohol with phosphorus halides. There are two phosphorus halides, phosphorus trihalide and phosphorus pentahalide. If I'm starting with the phosphorus trihalide, I start with 3 moles of the alcohol. Now, why 3 moles of the alcohol? Because the 3 R groups will take away the 3 halogen atoms to become 3 RX. Clear? What is remaining here? H3PO3. Then coming to phosphorus pentachloride. Now here I don't need to take 5, I only take 1 molecule. So whenever any compound containing oxygen reacts with PCl5, there are two products which are surely removed. One of them is POCl3. So phosphorus takes away the oxygen from alcohol and 3 chlorine atoms to form POCl3, phosphoryl chloride. This hydrogen takes away another chlorine to go out as HCl. Now we have already removed 3 plus 1, 4 chlorine atoms. What's remaining? RCl. RCl is what is formed. Coming to the last one, ROH plus SOCl2, thionyl chloride. Now, even here, one of the hydrogens takes away one of the chlorines to go out as HCl. SO will take away this oxygen to go out as SO2. What is remaining? R combines with the remaining Cl to form RCl. Now, this is something that we have seen in the previous chapter. This reaction is a favorable method for preparation of alkyl halides. We also understood why it is so, because both SO2 and HCl are vapors. They escape, leaving behind my alkyl halide. What is the name of this process? Yes, this process was called as Tarzan's process. So we studied this in the previous chapter. And what is the order of reactivity of hydrogen halides in the first case? Hi is more reactive than HBr, which is in turn more reactive than HCl, which means lesser the electronegativity of the halide or the halogen, more reactive it is. Or in other words, it's easy for us to break the bond between Hi than in the case with HBr than HCl. HF is generally unreactive. So I want to remember this as well. Now, one thing you need to understand, wherever during our lessons, wherever during our understanding, we come across orders, increasing order, decreasing order, reactivity order, and all those things, stability order, it's important that you know these are concepts that you have to keep in mind, both for pre-university as well as competitive, primarily more so for competitive, because in competitive you'll have questions like this: which of the following is most reactive, which of the following is least reactive, which of the following is most stable, which of the following is least stable, arrange the following in ascending order, arrange the following in decreasing order. So you will have all such kind of questions which will all be focused on the orders. So even before I tell you that it is important, any slide, any concept where you come across orders, make it a point that you think it is important. Okay, yeah. Coming to one other important reaction, which is based on the previous reaction, the Lucas test. Now, the Lucas test is a test that is used to distinguish between primary, secondary, and tertiary alcohols. Now, we have all seen in the first slide of this particular concept that all alcohols do not react the same. Different alcohols react differently. And who reacts the fastest? Tertiary reacts the fastest, followed by secondary, followed by primary. This test basically employs the same logic, but it is a test where we can visually see whether somebody is more reactive or not. Now let us understand. If somebody gives me 3 test tubes, and in all the 3 test tubes we have a liquid there, we have an alcohol. All of them look similar. You cannot distinguish them on the basis of their color. And they ask you, hey, please tell me which is primary, which is secondary, which is tertiary. All I need to do is very simple. I'll have to go to my shelf, take Lucas reagent, and add drops of the Lucas reagent to each of the test tubes. The moment I see a turbidity or cloudiness in a test tube, immediately after adding the few drops, I can confirm that that particular test tube contains a tertiary alcohol. If you see a cloudiness or turbidity after 5 minutes, you don't see it instantaneously, but you see it after 5 minutes, then that particular test tube contains a secondary alcohol. If you do not see any reaction at room temperature, no matter at any given point of time, after 5 minutes, after 10 minutes, after 10 hours, after 20 hours, you still don't see any reaction happening in the test tube, then you can be rest assured that that test tube contains a primary alcohol. Now, when do you see a test? When do you see a reaction? You'll only see a reaction upon heating. This is what is Lucas test. And for the Lucas test, we need a Lucas reagent. And who is that reagent? That reagent is anhydrous aluminum zinc chloride in concentrated HCl. So anhydrous zinc chloride in concentrated HCl is nothing but the Lucas reagent. Now, what is the reaction based on? Reaction is just based on what we studied in the previous slide. ROH reacts with the hydrogen halide HX, which is nothing but HCl here, in the presence of zinc chloride to give us an alkyl halide. Now, when is there a positive test? The solution should become cloudy. Now, if it is primary, there is no reaction. If it is secondary, reaction in 5 minutes. If it is tertiary, allylic or benzylic, reaction is immediate. Clear? This is at room temperature. Whereas if you want primary to react badly, then all you need to do is you need to heat it. The moment you heat it, primary will show a reaction with Lucas reagent. So this is one more important question. What is Lucas test, or explain Lucas test, or what is Lucas reagent? All of these have been asked. So in short, Lucas test is a test that is used to distinguish between primary, secondary, and tertiary alcohols. Tertiary alcohols give a reaction immediately. Secondary give a reaction after 5 minutes. Primary don't react at room temperature. Thereby, easily we can distinguish between primary, secondary, and tertiary alcohols. Now, the second reaction under this type is dehydration of alcohols. Now, remember, we came across a reaction to prepare an alcohol, hydration of alkenes. You remember that? Yeah, acid catalyzed hydration of alkenes, where you added water in the presence of an acid. We also looked at the mechanism there. Do you know what are the 3 steps to the mechanism? I gave you a shortcut to remember that as well. What was the shortcut? Yeah, please ask Dhoni. Protonation, attack of the nucleophile, deprotonation. We looked at all the 3 steps there, right? Yeah, if you have clearly understood that one, if you observe this reaction here, this reaction is just the reverse of that reaction, whatever we studied there. There, you started with an alkene, you ended with an alcohol. Here, you start with an alcohol and end with an alkene. Yeah, it is just the reverse of that. So, dehydration of alcohols. Now, this dehydration takes place in the presence of concentrated sulfuric acid at a particular temperature. You need to take excess of that acid. Now, what is the reaction here? We have seen that OH is removed, and along with OH, I need to remove H plus. Now, H plus are present at any of these places. I have so many H plus, but which H plus or which hydrogen do I remove? I will always remove hydrogen from the beta position. Clear? OH is removed from the alpha carbon atom naturally. The hydrogen should always be removed from the beta position. Hence, this reaction is also called as beta elimination. Clear? This reaction is also called as beta elimination. Beta elimination because the hydrogen is always eliminated from the beta position. So the moment OH minus and H plus is removed like this as water, what naturally happens is this bond shifts here. If this bond shifts here, I get the double bond giving me an alkene. Clear? Now, can you remember one more place where you came across this reaction? Think about it. We came across this particular reaction itself. The ones who would have practiced after the class, you'll be able to recollect. The others who just left it, you'll not be in a position to recollect. Yeah, some of you got it right. Yes. We came across preparation of ethers, remember? And in preparation of ethers, we came across dehydration of alcohols. We said the reaction can happen at 2 different situations, and the situation is determined by the temperature. At higher temperature, what do you get? At lower temperature, what do you get? Yeah, I know some of you are struggling with this. Go back to what we discussed in preparation of ethers. Remember, we spoke about 413 Kelvin, 443 Kelvin. At 2 different temperatures, 2 different products are obtained. This is one of the reactions there. Yeah, I want you to go back and read that reaction once again if you're not able to recollect that. All right? Yeah. Yes. Similar to hydration of alkenes, even for dehydration of alcohols, we need to know the mechanism. Very, very important once again. So in this chapter, we will come across two mechanisms. One is acid catalyzed hydration of alkenes, and the second one is dehydration of alcohols, again in the presence of an acid. So acid catalyzed dehydration of alkenes. One out of these two mechanisms will surely be asked in your exam. Clear? So I want you to focus on the mechanism here. As in the previous case, the first method is still, or first step is still protonation. Here, the alcohol is protonated. There, the alkene was protonated. Here, we are carrying out protonation of the alcohol with the help of H plus. So this H plus is unstable. Now, why is it unstable? It is unstable because it is deficient with respect to electrons. It needs electrons badly. So where will it get electrons from? It will take electrons from the lone pair, and using the lone pair, it will form a bond. So this is the bond that is formed. The moment the lone pair is used up, oxygen has lost that lone pair. Therefore, oxygen will get a positive charge. So this is the first step. So first step is nothing but protonation of alcohol. Coming to the second step. Now, whatever alcohol that we got, the protonated alcohol is unstable. Why is it unstable? It's unstable because it is having a positive charge there. Now, somehow this positive charge on oxygen has to be removed. There are two options here in front of oxygen. It can ask the hydrogen to go out, which took away the lone pair. So if this hydrogen goes out, this lone pair will go back on oxygen and giving us back what? Giving us back the alcohol. But is that what we want? No, that's not what we want, which means this will not happen. Instead, what is going to happen is the bond is broken here between carbon and oxygen. The moment the bond is broken, these two electrons will go on oxygen to become the lone pair, and this entire species goes out as water. So in the second step, water is removed. After the removal of water, after breakage of this bond, the resultant species is a carbocation because there is a positive charge on this carbon. So hence the second step is called carbocation formation. Clear? Coming to the last step. In the last step, this carbocation is unstable. Now, why is it unstable? It's unstable because the carbon is deficient with respect to electrons. So there's only one way in which it can get back its valency or remove that positive charge. One of the hydrogen should move. Now, if this hydrogen moves, say for example, if this hydrogen moves, this bond will come inside. Now, if this bond comes inside, there is a problem. What is the problem? This carbon will have 5 bonds around it, and this carbon will still be having 3 bonds around it. Hence, I cannot remove a hydrogen from the alpha carbon. Hence, hydrogen is always removed from where? It is always removed from the next carbon, which is my beta carbon. So hydrogen is removed from the beta carbon as H plus, which is what is this? It is going out as H plus. The moment it goes out as H plus, there is this bond here. The electrons of this bond will go inside to form the double bond. Hence, we get back the ethene. Now, when this happens, both the carbons are happy with respect to the valency. Clear? Now, do you understand why it is always the beta hydrogen that has to be removed and not the alpha hydrogen? This is the reason. Clear? And what's happening in this step? In this step, there is removal of H plus, which is nothing but deprotonation. So deprotonation of the carbocation results in the formation of ethene and giving away H plus. Now H plus was used up in the first step. H plus is got back in the last step. Hence H plus behaves as what? Yes, H plus behaves as a catalyst. So these are the three steps. So which are the three steps? First step, attack of H plus protonation to give us this species. Second step, removal of water forming the carbocation. And the last step is removal of H plus to form the ethene. Now, this was the shortcut that we used for the previous mechanism. Which mechanism was that? Acid catalyzed hydration. Please ask Dhoni. Protonation, attack of the nucleophile, deprotonation. Now, can you use the same thing? Unfortunately, you cannot use the ask here because the second step is nothing but carbocation formation. So how do you modify this? Whereas protonation, deprotonation remains the same. So please and Dhoni can stay. Somehow I need to change this. So one of the things that I did was, please instead of ask, I will be using call. Please call Dhoni. Now here C will be nothing but the second step, carbocation formation. Clear? So which means the same similar shortcut can still be used, except that the second step will be carbocation formation instead of attack of the nucleophile. So if you remember, please call Dhoni, you will be able to remember this mechanism. Clear? So like the previous homework that I gave you, I want you to write this mechanism 3 times. Now when you're writing this mechanism, see there are two ways in which you can write your homework. Point number one, for the sake of submission. Oh, just because this person has told me in the class, just because there should be a confirmation that I am in the class or not, I need to submit it. Oh, I need to submit it, otherwise I need to face consequences. Oh, if I don't submit it, I need to get shouted at by somebody. No, don't look at life that way. Don't look at homework that way. Look at homework to build your understanding. The reason why I'm giving you a homework is not to test you, not to punish you, not to torture you. The reason I'm giving you the homework is because, at least for the sake of the homework, if you go back and practice, then you will be thankful for whatever work was given to you. Clear? So it's all about how we choose to do things. You can choose to take something as a torture, or you can choose to work on it so that you can get better. And the sole purpose of all my homeworks will not be to torture you, will be to only ensure that you master organic chemistry better than anybody else. Clear? So take this as homework, write it 3 times, and I want you to write the first time looking at the mechanism. The next 2 times, write it without looking at the book, without looking at the slide. Only then you will understand where all you will make mistakes. Whereas most of the times when we're completing the homework, we'll just look at the literature, we'll look at whatever we were written in the book, we'll look at the slide and then copy happily, word to word, letter to letter, arrow to arrow, we'll happily copy. But is that going to help you? No, it is only going to help you by submitting your homework in time. But is that the objective? That is never the objective. So please understand, this is not only applicable for homework, this is applicable for life as well. You have a choice with which you can look at life. You can look at life as torture, or you can look at life as an opportunity. Whatever way you choose, you will face the exact consequences for the same. Clear? So wonderful. We will stop for today. I want you to write the homework and submit it within time. As always, I'll give you 1 hour this time, or let me be a bit conservative. I'll still give you 1.5 hours. Within a 1.5 hours, I want you to finish today's homework and submit it in the class. Clear? So until the next class, thank you. Namaste.